Hi, I'm Mindy from Apex Tutoring. Today we're going to work through the 2022 HSC Mathematics Extension 2 exam. I'll be assisted by the brand new Casio FX 8200 AU. Let's get started. Question 1. Let R be the region in the complex plane defined by the real component of Z is between 1 and 3, including 3, and the argument of Z is between pi over 6, including, and pi over 3. Which diagram best represents the region R? So, we have a number in the complex plane. Its real component is between 1 and 3, and we're including 3. So, if we look at our options, all of them include parts of the complex plane between 1 and 3 on the real axis, which is the horizontal axis. Although, we are meant to include 3 but not 1. So we want to see a solid line along 3 and a dashed line at 1. So that narrows down our options to A and C. Now the argument, as in the angle of rotation in the positive horizontal axis, is between pi over 6 and pi over 3, including the pi over 6 but not the pi over 3. So we want to see a solid line for that smaller angle of pi over 6 and a dashed line for that larger angle of pi over 3. So that means the correct answer will be A. Question 2. The following proof aims to establish that -4 is equal to 0. At which line is the implication incorrect? So the proof says, let A equal -4. Then in line 1, we have A squared equals 16, and 4A plus 4 equals -12. Both of those statements are true if A is -4. Line 2 says A squared plus 4A plus 4 equals 4. What we've done between line 1 and line 2 is add these two equations together, the left-hand sides and the right-hand sides. And so line 2 is also a true statement. Line 3, in a bracket, A plus 2, which is squared, is equal to 2 squared. So both sides have been factorized. The left-hand side, a perfect square quadratic. The right-hand side, we're rewriting 4 as 2 squared. So line 3 does follow from line 2. Now line 4 says that then A plus 2 must equal 2. This is where the problem comes in, because to get from line 3 to line 4, we would need to square root both sides. And you may recall that when we do that, we're told to put a plus or minus on the result. Now the reason for that is because the square root of x squared isn't x, it's actually the absolute value of x. So for example, if the absolute value of x is equal to 2, that would mean that x itself would equal plus or minus 2. So line 4 is where the problem comes in. The next line, of course, is the conclusion that A equals 0, but line 4 has an error in its logic. So the answer to question 2 is D. Question 3. Let A, B, P be 3 points in 3-dimensional space with A not equal to B. Consider the following statement. If P is on the line AB, then there exists a real number lambda such that the vector AP is equal to lambda times the vector AB. Which of the following is the contrapositive of this statement? Okay, so for a conditional statement such as if P, then Q, the contrapositive is if not Q, then not P. And we know that a conditional statement is true if and only if its contrapositive is true. So let's identify the P and the Q in this conditional statement. So we have if P is on the line AB, then Q will be there exists a real number lambda such that Now we have to take their inverses and flip it. So, what is not Q? Or what is the opposite of there exists a real number lambda such that the vector AP is lambda times the vector AB? But if we look at our options, we have to see what is logically equivalent. In the first option, it says for all real numbers lambda, and then that equality statement. That's not what we're looking for. The opposite of there exists a real number is not for all real numbers. But in part B, it says if for all real numbers lambda, vector AP is not equal to lambda times the vector AB, that means there does not exist a real number lambda such that that's true. So this first part is equivalent to not Q. And of course, we need then not P. Of course, what's the opposite of P is on the line AB? Well, P is not on the line AB. And so we have here not P. If we want to check the other two options, C and D, the antecedent of each of these statements is not equivalent to not Q in this situation. If there exists a real number lambda such that AP is equal to lambda AB, that's pretty much Q, not Q. And if there exists a real number lambda such that vector AP is not equal to lambda times vector AB, well, that statement is not the opposite of our Q statement, because in our Q statement, there just needs to be a real number lambda, which means that if that is true, there can still exist a real number lambda that does not make that equality true. So C and D are definitely not options here. So the answer is B. Question 4. Of the following expressions, which one need not contain a term involving a logarithm and its antiderivative? So for option A, we can see that the numerator can easily be turned into the derivative of the denominator. It's simply missing a factor of 2. So we could express that as 1/2 times 2x plus 4 over that denominator. And that would definitely involve a logarithm then as its antiderivative. Option B, the denominator here is factorizable. So we could write that as x minus 5, x plus 1. And then we could do something like partial fraction decomposition to express it in the form a over x minus 5 plus b over x plus 1. So that one will definitely involve logarithms. Option C, we could factorize the denominator using factorization by parts. And we could see that would simplify. And the antiderivative then would involve an inverse tangent, not a logarithm. So that's probably our answer. If you want to consider option D, we can similarly factorize the denominator. And if we wanted to integrate, we'd have to do maybe partial fraction decomposition again. Because we do have an irreducible quadratic in that denominator, one of them will be linear, and the other are constants, which would involve a logarithm for that part. So that confirms that the answer is C. Question 5. If the integral from a to x of f of t dt is equal to g of x, which of the following is a primitive of f of x times g of x? Now this equality here in the question means that g of x is the primitive of f of x. To demonstrate, if we took the derivative on both sides with respect to x, on the left-hand side, that would equal to f of x by the fundamental theorem of calculus. The right-hand side, of course, is the derivative of g. Now, if we want to find the primitive of f of x times g of x, we would be looking at integration by parts. we'll make u g of x, since we now know the derivative of g of x is f of x. And so the primitive would be u times v, so g of x times itself, g of x squared, minus the integral of v du, which is g of x times f of x dx. So this is a typical result where we get the same integral after we do the integration by parts. So what we do is we add that integral to both sides of this equation, as in this is the left-hand side and this is the right-hand side. That would give us that 2 times the integral is equal to g of x squared. And that tells us that the integral that we are looking at is equal to 1/2 times g of x squared. So the answer is C. Question 6. It is known that a particular complex number z is not a real number. Which of the following could be true for this number z? So z is an arbitrary complex number that is not real, which means that its imaginary component is not 0. So let's say z is some real component plus an imaginary component times I, where again the imaginary component is non-zero. Now 2 of the options involve I times z, so let's consider what happens if we do that. We would get its real component becomes the negative of the imaginary component, and the imaginary component would be equal to the real component of the original number. So could something like option A be true? That this could equal the conjugate of z? Well, the conjugate is what we get if we make z's imaginary component negative. So this could be true if the negative of the imaginary component of z is equal to the real component of z, and the real component of z is equal to the negative of the imaginary component of z, which is just a restatement of the same thing. So that could indeed be possible if the imaginary component of z is non-zero. Let's consider the other options. Option C involves I times z. So could the real component of I times z, which is the negative of the imaginary component of z, equal the imaginary component of z? And that's not possible if the imaginary component of z is not 0. So we can rule out option C. Now let's look at option B, since it involves the conjugate, which we have written here. Could this equal the modulus of z squared? Well, the modulus of z squared would be a real number. And if z is a complex number whose imaginary component is not 0, then its conjugate would also be a complex number whose imaginary component is non-zero. It could not equal simply a real number. So B is not going to be an option. And then let's look at option D. So if we look at option D then, this is about the arguments of z and z cubed. Could the argument of z cubed be equal to the argument of z? Well, we know from things like de Moivre's theorem that the argument of z cubed is equal to 3 times the argument of z. So when would this equality be possible? So another consequence of z not being a real number is that its arguments cannot be 0 or pi. And if you think about that statement that 3 times the argument is equal to the argument, that would only be true if the argument is 0 or pi. Now, of course, 3 times 0 is 0, but when it comes to rotations around the complex plane, a rotation of pi would be equivalent to a rotation of 3 pi. And this wouldn't work in any other circumstances for any other angles. So D is not an option, which confirms the answer is A. Question 7. Consider the statement P. P is for all integers n greater or equal to 1. If n is a prime number, then n times n plus 1 divided by 2 is a prime number. Which of the following is true about this statement and its converse? Okay, for a conditional statement, such as if A, then B, the converse is if B, then A. Now, if the first statement is true, that does not necessarily mean the other is true, and vice versa, so we'll have to evaluate each of these separately. So to test the converse statement, we will need to figure out what that is. Let's identify the A and the B parts of statement P. So the antecedents is for all integers n greater than or equal to 1 if n is a prime number, and then the consequence is n times n plus 1 over 2 is a prime number. So we just swap those around to create the converse. It would be if n times n plus 1 over 2 is prime, then n is a prime number for all integers n greater than or equal to 1. Let's check the truth of each of these statements. Now, a quick way to disprove a statement would be to find a counterexample, although the job then comes down to finding that counterexample. If we think through a few prime numbers, we might be able to work out something that disproves statement P. If you try 2, it's actually true for 2 because you'd have 2 times 3 over 2, which is prime. If you try 3, you would have 3 times 4 over 2, which is 6, which is not prime. So we have proven that P is not true. What about its converse? So let's further consider this statement here and what it means for it to be prime. So we know classically that n and n plus 1 will have to be even, 1 will have to be odd. If n is meant to be a prime number, the only time n will be even is for n to equal 2. And we already tested that actually. That would be 2 times 3 over 2, which is 3, which is prime. And both n and n times n plus 1 over 2 is prime, so it's true in that case. So then, otherwise, if n is a prime number, it will be an odd number, which means n plus 1 is even and greater than 2. So that means if we're looking at n times n plus 1 over 2, n plus 1 has to be an even number greater than 2, and so we can express n plus 1 as something times 2, maybe k times 2, which means this will be n times k, which means there will be no other time when this is a prime number. So the converse is actually true because n times n plus 1 over 2 is prime only actually when n is 2, and in that case, n and that thing are prime, and there are no other times where it needs to be tested to be true. So we can say that the answer is D. We know the statement is P is false, but its converse is true. Question 8. As a projectile of mass m kilograms travels through the air, it experiences a frictional force. The magnitude of this force is proportional to the square of the speed v of the projectile. The constant of proportionality is the positive number k. The position of the particle at time t is denoted by the vector x, y. The acceleration due to gravity is g meters per second squared. Based on Newton's laws of motion, which equation models the motion of this projectile? Let's start with F equals ma. What are our forces? So we have gravity, It only acts in the vertical direction. And then we have air resistance. Let's break that down into the horizontal and vertical components. It's going to be proportional to the square of speed. To get the horizontal component of the square of speed, we'd have to multiply it by cosine of angle theta. Now, theta can change over time, so theta is a function of time, but we could write it this way. Similarly for vertical. And acceleration, of course, on the right-hand side. Now, what can we do with that second vector there? Well, we do know that v cosine of theta and v sine theta would equal to the horizontal component for velocity with respect to time, since again theta is a function of time, and the vertical as well. So we can rewrite that second vector by using one of the factors of v in v squared to create the vector for velocity. And then if we pull out that constant kv from that second vector, we will get answer B. Question 9. Let A and B be two distinct points in three-dimensional space. Let M be the midpoint of AB. Let S1 be the set of all points P such that the vector AP dot the vector BP equals 0. Let S2 be the set of all points N such that the length of the vector AN is equal to the length of the vector MN. The intersection of S1 and S2 is the circle S. What is the radius of circle S? To help me work through questions like this, I like to draw a diagram. We have 2 points AB and M is the midpoint. Now let's consider S1, the points P, such that the vector from A to P dotted with the vector from B to P is equal to 0. Remember, what that means is that those two vectors are perpendicular. So where would all the points P lie such that the vector from A and B to that point is at a right angle or perpendicular? I could sketch a few examples. So right now, it looks a bit 2D, and it looks like P would, of course, form a circle. However, this is in 3D space, so you can imagine rotating this and having the same thing all the way around. So P, the points P actually form a sphere where AB is a diameter and M is the center. Let's consider S2. So the points N where the length from A to N is equal to the length from M to N. So one example of these points would be just halfway between A and M, the midpoints. And then we could draw similarly and of course it looks a bit 2D. So we could draw these all in a straight line, but it can also be rotated around. And so this is going to form a plane that intersects the sphere, which of course, when they cut each other, will form a circle. So let's take one of those points of intersection of that plane and that sphere. From that center point, we can go straight out to the sphere. Now the circle would be going around the sphere like that. The radius is this length here. we need to work out its length. We can see that a right triangle can be formed. And let's also remember those points on the sphere were generated at right angles between AP and AB. So I can sketch what we have. And once again, we want to find this length here. So this length here is 1/4 of the length from A to B, since it's halfway between the midpoint and A. We also then have that this length here is 3/4 of the length of AB. Now, you may notice that we have some similar triangles here. This triangle here is similar to this triangle here, since their angles are the same. So we can set up some ratios to solve for R. In the yellow triangle, I'd have R over 1/4 the length of AB is equal to 3/4 the length of AB over R. This would result in R squared equaling 3/16 times the length of AB squared, and if we squared both sides, we get R is the square root of 3 over 4 times the length of AB. So the answer is D. Question 10. A particle is moving vertically in a resistive medium under the influence of gravity. The resistive force is proportional to the velocity of the particle. The initial speed of the particle is not 0. Which of the following statements about the motion of the particle is always true? So once again, a diagram could be helpful here. There's two possible situations. The particle is initially moving up or initially moving down. We have a downward force of mg and a force in the opposite of the direction of travel, which is kv, since it's proportional to the velocity. So option A says if the particle is initially moving downwards, then its speed will increase. Now, that would happen if mg is greater than kv given the initial velocity. So it could be true, but may not always be true. And for option B, if the particle is initially moving downwards, then its speed will decrease. So that would happen if kv was greater than mg, but again, that depends on initial velocity and may not always be true. So then option C is, if the particle is initially moving upwards, then its speed will eventually approach a terminal speed. And let's compare that to option D. If the particle is initially moving upwards, then its speed will not eventually approach a terminal speed. So if it is initially going upwards, then both the gravity and the resistive force will be acting in the opposite direction of its travel. So at some point, it will reach a speed of 0, and then it will start coming back down. Since that change of direction means it will reach a speed of 0, we know that initially mg is stronger than kv. So it will accelerate downward until mg and kv are equal, at which point it will reach a terminal speed. So option C is the right one. Question 11a. Express 3 minus I over 2 plus I in the form x plus iy, where x and y are real numbers. Okay, so what we need to do here is multiply the numerator and denominator by the conjugate of the denominator. So we'll expand. Those middle two terms on the denominator cancel as it's a difference of squares. Remember, I squared is -1. So the answer is 1 minus I. Now, before we move on, I wanted to show you what you can do with a Casio FX8200AU in terms of working with complex numbers. So, it is a 2-mark question, so you still need to do the working out, but you could check your answer here to question 11a. Here's how you put that in. Here's how you do that. So, go to the home screen if you're not there already, and go to complex mode. Now, we wanted to express 3 minus I over 2 plus I as one complex number. So, we can put in a fraction and type in 3 minus I. You'll see pi above the 7, e above the 8, and I above 9. So if we do shift 9, we'll have 3 minus I in the numerator. Then in the denominator, we'll put 2 plus I. And you can see that we got 1 minus I. So that helps us have confidence in our answer. 11b. Evaluate the integral of sine cubed of 2x times cosine of 2x dx. So to do this integral, we're going to use the fact that the derivative of a sine is cosine, and we're going to use a u substitution where u is sine of 2x. Then du would be 2 cosine of 2x dx, and so we can replace cosine of 2x dx with 1/2 du. So we can now write this integral as the integral of u cubed times 1/2 du, which becomes 1/2 times u to the 4th over 4 plus c. And simplifying, that will be 1/8 u to the 4th plus c. Now, don't forget to substitute back in so that our answer is in terms of x. So we have 1/8 sine to the 4th of 2x plus c. Question 11c. Part 1 is to write the complex number of -√3 plus I in exponential form. So, to write a complex number in exponential form, we'll need its modulus and its arguments. So its modulus would be the square root of the real component squared plus the imaginary component squared. And we get 2. The argument can be found by considering that tan of the argument is equal to the imaginary component over the real component. Since the real component is negative and imaginary positive, we know that we are in quadrant 2. We can check where tan would equal 1/√3 by looking at our triangles, and that would be at 30 degrees or pi over 6. In quadrant 2, this would be 5 pi over 6. So this complex number is equal to 2e to the 5 pi over 6 times I. Okay, before we moved on, I wanted to show you what you could do with the Casio FX 8200 AU in this question. So, if we want to express a complex number which is currently in rectangular form and put it into exponential or polar form, we'd first put it into the calculator. So here I'll put -√3 plus I and hit equals or execute to put that in as the answer. Now, if you click on Format, which is next to the equals button, you can convert this into different forms. So if I go to polar coordinates, hit OK, I now see 2 with the angle symbol 5 over 6 pi. So that means that the modulus is 2, and the argument is 5 pi over 6, which matches what we got in this question. Now C part 2 is hence find the exact value of -√3 plus I to the power of 10, giving your answer in the form x plus iy. So having a complex number in exponential form makes it much easier to find a power of that number. Now, we might want to convert that argument to a principal argument and then convert back into x plus iy form. 3 goes into 25 8 times. So we would make 4 revolutions and then have 1/3 of a pi left over. Now, the real component would be 2 to the 10 cosine of pi over 3, and the imaginary component, similarly, 2 to the 10 times sine of pi over 3. Now, on our triangles, we can see that cosine of pi over 3, 60 degrees, is a half. Sine is root 3 over 2. So simplifying, x would be 2 to the power of 9, y would be 2 to the power of 9 root 3. So the answer is 2 to the power of 9 plus I times 2 to the power of 9 root 3. Now, before we moved on, I wanted to show you what we could do on the Casio FX8200AU. So, if we'd like to take a complex number to a power, we could do that in polar/exponential form or in rectangular form. So let's say we want to enter a complex number in polar or exponential form. So I'll start by putting the modulus, in this case 2. Next, we need that angle symbol. So if you go to catalog and go to complex, you have a few operations here that could be useful for us. And we have 5 pi over 6. Now you can see that automatically what the calculator wants to do is put that into rectangular form for us. Let's see how we would take a power of that complex number. Now, it's not exactly in the form we want, but it could help us double check our answer. We could check 2 to the power of 9 and 2 to the power of 9 times the square root of 3 to verify that we would have 512 for the real and 886.8 or so for the imaginary components. Again, don't forget to show all of your working out when you're working on your test. It's important to show your working so you can get full marks. But your calculator can be very helpful to you in checking your answers and even sometimes in the problem-solving process. Question 11D. A triangle is formed in 3-dimensional space with vertices A, 1, -1, 2, B, 0, 2, -1, and C, 2, 1, 1. Find the size of angle ABC, giving your answer to the nearest degree. Okay, if you like, you could draw a diagram to help organize things. So this would be A at 1, -1, 2. This would be B at 0, 2, -1. And this would be C at 2, 1, 1. We want the angle ABC to the nearest degree. We know we can find the angle between two vectors using the dot product. So let's set up vectors between some of these points. What's the vector from B to A? Each component is the end point minus the beginning point. So the x component will be 1 minus 0, the y component, -1 minus 2, and the z component, 2 minus -1. So 1, -3, 3. How about from B to C? That'll be 2 minus 0, 1 minus 2, and 1 minus -1. So that's 2, -1, 2. Now, the formula sheet has some things about dot products on it. Go to the section on vectors, and we're going to use this. U dot V is the length of U times the length of V times cosine of angle theta. So let's find the length of BA. That'll equal the square root of 1 squared plus negative 3 squared plus 3 squared, the square root of 19. Let's find the length of BC. So that's the square root of 2 squared plus negative 1 squared plus 2 squared, square root of 9, which is 3. So we'd have 3 root 19 times cosine of the angle between them is equal to their dot products, which we can do as the product of each of their components added together. So 1 times 2 plus negative 3 times negative 1 plus 3 times 2. So solving for cosine theta, we'd have 11 over 3 root 19. So what's theta? We want it to the nearest degree, so make sure we're in degrees mode. And we'll take inverse cosine of 11 over 3 root 19. To the nearest degree, that would be 33 degrees. Question 11e. Let L1 be the line with equation xy equals negative 1, 7 plus lambda times 3, 2, where lambda is a real number. The line L2 passes through the point A, negative 6, 5, and is parallel to L1. Find the equation of line 2 in the form y equals mx plus c. Okay, L2 needs to be parallel to line 1. That means it needs to be going in the same direction. And the direction vector, much like the gradient, is this one here that is multiplied by our parameter lambda. That will tell us the gradient of our parallel line. The gradient will be 2 over 3. Remember, it's change in y over change in x. The y component is 2, and the x component is 3. And our point goes through negative 6, 5. Now we just need to create the equation of that line. We can use point gradient form. So we get y equals 2/3 x plus 9. Question 11f. Using the substitution, t equals tan x over 2, find the integral of 1 over 1 plus cosine x minus sine x dx. Okay, let's start with that t substitution. Maybe first we'll find out what dx is by taking the derivative here. Now solving for dx, 1 over secant squared is cosine squared. Now we also need to replace the cosine and the sine. Let's use the t formulas. So according to the t formulas, sine will be 2t over 1 plus t squared, and cosine will be 1 minus t squared over 1 plus t squared. We'll also need to fully express dx in terms of t. So we'll need to use the double angle formula here. This down here will help us to express dt solely in terms of t. And that's because inside the cosine now is a double. Now we'll just substitute in the t formula. And maybe simplify. . All right, so we're ready to substitute everything in. So to simplify, I'll multiply the numerator and denominator by 1 plus t squared. So this will equal the negative of ln of 1 minus t plus c. Now we still need to substitute back in so that our answer is in terms of x. And t was tan of x over 2. So our answer is negative ln of the absolute value of 1 minus tan of x over 2 plus c. Question 12a. For real numbers a and b greater than or equal to 0, prove that a plus b over 2 is greater than or equal to the square root of ab. Okay, some may recognize this as the AM-GM inequality. So to prove this, we start with the square root of a minus the square root of b squared is greater than or equal to 0. A known fact, since a square has to be greater than or equal to 0. Then we'll expand. Next, we're going to add the 2 root ab to the right-hand side and divide by 2. And so the result is proven. 12b. A particle is moving in a straight line with acceleration a equals 12 minus 6t. The particle starts from rest at the origin. What is the position of the particle when it reaches its maximum velocity? So, we know that the maximum velocity will occur when the acceleration is equal to 0. Now, to verify that this is a maximum, we can consider the sign of A. It's a line with an intercept of t equals 2, and it's got a negative gradient. Before 2, it's positive, increasing. After 2, it's negative, decreasing, which verifies that is a mass. Now we need the position of the particle when t is 2. Now we can get the velocity by integrating the acceleration with respect to time. Now the particle starts at rest. So when t is 0, v is 0. So c is 0 in this case. I might label that as c1 because later we might have another. Now position will be the integral of velocity. Now the particle starts at the origin, so when t is 0, the position is 0. So when t is 0, x is 0. So c2 is 0. So the position will be at t equals 2, equals 12. Question 12c. A particle with mass 1 kilogram is moving along the x-axis. Initially, the particle is at the origin and has a speed of u meters per second to the right. The particle experiences a resistive force of magnitude v plus 3v squared newtons, where v, meters per second, is the speed of the particle after t seconds. The particle is never at rest. Part 1, show that dv dx is equal to negative of 1 plus 3v. Okay, so with questions like this, we need to start with acceleration. So in this case, our acceleration is due to the resistive force. That'll be negative v plus 3v squared. Now, if we look at our reference sheet, we have that acceleration is equal to v dv dx. And we'll divide by v. And that's the result. Now part 2, hence or otherwise find x as a function of v. To find x as a function of v, we're going to take that expression we have from part 1, and we'll treat it as a differential equation. We can separate the variables and integrate both sides. Now, since v is greater than 0, we don't need these absolute values. So we can write ln of 1 plus 3v equals negative x plus c. Now, we were given that initially the particle is at the origin with a velocity of u. So we have ln of 1 plus 3v equals negative x plus ln of 1 plus 3u. Now to solve for x, we'll swap these terms to get x is equal to ln of 1 plus 3u minus ln of 1 plus 3v, which we would typically express as ln of 1 plus 3u over 1 plus 3v. Question 12d. Using partial fractions, evaluate the integral from 2 to n of 4 plus x over 1 minus x times 4 plus x squared dx, giving your answer in the form of 1/2 ln of a function of n over 8 times n minus 1 squared, where f of n is a function of n. Alright, let's start with partial fractions. So one of the factors in the denominator is an irreducible quadratic. So our numerator could be linear. The other factor is linear, so the numerator would be a constant. Now the way I work these out is I multiply everything by the full denominator on the left. On the left-hand side, we just get 4 plus x. On the right-hand side, for that first fraction, the 4 plus x squared cancels, so we get ax plus b multiplied by 1 minus x. And then on that second fraction, the 1 minus x cancels, so we get c times 4 plus x squared. Then I start with letting x be a number that will make one of the factors 0, such as x equals to 1. The left-hand side will be 4 plus 1, which is 5. The right-hand side will be a times 1 plus b times 0 plus c times 4 plus 1 squared, which is 5. This simplifies to 5c equals 5, which gives us c equals 1. Now, we're out of brackets that could be 0, so we'll pick another number for x, something simple like x equals to 0. If x equals 0, the left-hand side is just 4. The right-hand side, a times 0 will be 0, so we'll just have b times 1 minus x, which is just 1, plus c, which we found out was 1, times 4 plus 0, which is 4. So we get b plus 4 equals 4, which tells us b is 0. I'll pick another number for x, perhaps x equals to negative 1. The left-hand side will be 4 minus 1. The right-hand side will have a times negative 1, so negative a plus b, which is 0, times 1 minus negative 1, which is 2, plus c, which is 1, times 4 plus negative 1 squared, which is 5. So we get negative 2a plus 5 equals 3. So we get a is 1. So the first fraction, ax plus b, a is 1, b is 0, just becomes x over 4 plus x squared. And the second fraction, c over 1 minus x, c is 1, so that's just 1 over 1 minus x. So for that first fraction, we'll use a logarithm. We need a derivative of the denominator and the numerator. We're missing a factor of 2. So we'll times by 2 and by a half. And the second one will be a logarithm, which is missing the factor of negative 1. So we'll put a negative here and here. So this will be ln of the absolute value of 4 plus x squared with a 1/2 in front minus ln of the absolute value of 1 minus x. And we're going from 2 to n. Now since x starts at 2, we don't technically need those absolute values. So we'll start by plugging in n. Now notice how n is greater than 2. So 1 minus n will always be negative. The absolute value would make that be positive. Another way to make that negative positive is to multiply it by negative 1. Now we'll plug in 2. And simplify. And I'll just note that I dropped the absolute value on this expression because 4 plus n squared would always be positive. And ln of 1 is 0. Now, if we look back at what we need, we have a 1/2 in front of the entire log. So let's factorize out 1/2 before we proceed. And then use log loss to simplify. And we have the results. Question 12e. Given the complex number z equals e to the I theta, show that w equals z squared minus 1 over z squared plus 1 is purely imaginary. Okay, let's consider the polar form of z in this expression of w. Since z is squared, the argument will be 2 theta. Let's get the reals together and the imaginaries together. We could use double angle identities here in both the real and imaginary components. I factorized the negative out of the top left so that it would match the top one here and the double angles for cosine. Now let's factorize. Note that the 2's cancel. Now, in the numerator, if I factorize out an I, this is what I'll get, and negative 1 over I is equal to I. And that's because if I simplified it by timesing the top and bottom by I, I'll get negative I over I squared, and since I squared is negative 1, that just equals I. So simplifying, this becomes sine over cosine, which is tan, times I, times 1, since the numerator and denominator brackets are the same. Since tan theta is a real number, I times tan theta is an imaginary number, purely imaginary, we have no real components. Question 13a. Prove that for all integers n with n greater than or equal to 3, if 2 to the n minus 1 is prime, then n cannot be even. So let's simplify what we have to prove. Now, this statement seems a little bit difficult to prove going forwards. Perhaps the contrapositive would be easier to work with. And that's because it's easy to start with an even number and then see what happens to it in an expression like 2 to the n minus 1. So if n is even, then we can express n as something like 2 times k, where k itself is an integer. Since n has to be greater than or equal to 3, k has to be greater than or equal to 2. So let's see what happens in 2 to the n minus 1. Note that this could be looked at as a difference of squares. Since this can be expressed as the product of two distinct numbers, we can say that this is not a prime number. And since the contrapositive is true, the original statement is also true. Question 13b. The numbers an for integers n greater than or equal to 1 are defined as a1 is the square root of 2, a2 is the square root of 2 plus the square root of 2, all inside the square root, a3 is the square root of 2 plus the square root of 2 plus the square root of 2, all nested, and so on. These numbers satisfy the relation an plus 1 squared equals 2 plus an for n greater than or equal to 1. Use mathematical induction to prove that an equals 2 cosine of pi over 2 to the n plus 1 for all integers n greater than or equal to 1. So, our proof needs to start at n equals 1. So by the first definition, a1 is the square root of 2. By the second definition, that will equal 2 times cosine of pi over 2 to the 1 plus 1, which is 2. Now cosine of pi over 4 is 1 over root 2. If we rationalize, we get 2 root 2 over 2, which is equal to the square root of 2. So it's true for n equals 1. Now we assume it's true for some n equals k. Now, it'll be difficult to express something like this for the kth term. So let's use this relation to express ak. So what we'll say is ak plus 1 squared equals 2 plus ak, where ak is equal to 2 cosine of pi over 2 to the k plus 1, and a1 is the square root of 2, the first term of that relation. And putting that together means ak plus 1 squared equals 2 plus 2 cosine pi over 2 to the k plus 1. Now we see if we can prove it's true for n equals k plus 1. So now we need to show that a, k plus 1, so k plus 2, squared equals to 2 plus a k plus 1, where a k plus 1 is 2 times cosine of pi over 2 to the k plus 1, so k plus 2. So the full equation we want to show is true is a k plus 2 squared is equal to 2 plus 2 cosine of pi over 2 to the k plus 2. So let's see what we can do. So our left-hand side, a k plus 2 squared, by the definition of the relation, is equal to 2 plus a k plus 1. Now, according to our assumption, that would equal to 2 plus, now in our assumption, a k plus 1 is squared, so I'll have to write the square root of 2 plus 2 cosine of pi over 2 to the k plus 1. Maybe what's inside that square root reminds you a little bit of the double angle identities for cosine. So let's take a look. So we'll be able to express what's inside that square root in terms of cosine squared. We just needed to say 1/2 times 1 plus cosine of 2 times something. So if we factorize out 4, we'll be left with 1/2 times 1 plus cosine. Now inside the cosine we want it to be double of something, so let's times by 2 and 1/2 at the same time. Now that will become pi over 2 to the k plus 2. And we can square root. And that is actually the right-hand side we were looking for. So by the principle of mathematical induction, the statement is true. Question 13c. Consider the equation z to the power of 5 plus 1 equals 0, where z is a complex number. Part 1. Solve the equation z to the 5 plus 1 equals 0 by finding the fifth roots of -1. Okay, let's rearrange that equation and solve for z to the power of 5. And that's why finding the fifth roots of -1 will give us the solutions for z. We're going to express -1 as a complex number in polar or exponential form. Now, of course, -1 has an argument of pi. But so we can get all 5 roots, we get 5 equivalent arguments by adding 2 pi to this 4 more times to generate 5 equivalent expressions for -1. So we'll have 3 pi, 5 pi, 7 pi, and 9 pi. And then we take everything to the power of a fifth to solve for z. Notice that 7 pi over 5 and 9 pi over 5 are past pi, so we can express them as a principal argument by subtracting pi. And so our solutions are e to the minus I times 3 pi over 5, e to the minus I times pi over 5, -1, again, e to the I pi is -1, e to the I times pi over 5, and e to the I times 3 pi over 5. Part 2. Show that if z is a solution of z to the 5 plus 1 equals 0, and z is not equal to -1, then u equal to z plus 1 over z is a solution of u squared minus u minus 1 equal to 0. Let's substitute that expression for u in terms of z into that quadratic and see what happens. Let's expand. We'll just simplify it a little bit. And let's get that all into one fraction. Now, where does z to the fifth come in? Well, you may recognize in that numerator a special kind of factorization we see sometimes. If we multiply the numerator by z plus 1, it will simplify down to z to the fifth plus 1. So let's times the top and bottom by z plus 1. Now, we were given that z is a solution to z to the fifth plus 1, where z is not equal to negative 1. And so, since z does make that numerator equal to 0, it is a solution to the original quadratic. And of course, having z plus 1 in the denominator isn't an issue because in our situation, z is not the root negative 1. Part 3. Hence, find the exact value of cosine of 3 pi over 5. Okay, when we get questions relating trigonometry, identities, and complex numbers, we usually then need to express the complex number in polar form. Now, 3 pi over 5 was one of the arguments of the roots of negative 1. So we're going to, in this case, let z equal cosine 3 pi over 5 plus I sine 3 pi over 5. And we'll be able to plug it into that quadratic since we've proven that z is a solution to that quadratic when z is a solution to z to the 5 plus 1. We can also use the shorthand CIS 3 pi over 5 to represent cosine plus I sine. So we can put this into that quadratic in the form of z plus 1 over z. Now, we could rewrite this. So 1 over each of those complex numbers will equal the conjugate of that complex. Then if we consider cosine plus I sine plus the conjugate of the same thing, the imaginary components will cancel and we'll have 2 of each of the real components. Now, this is a quadratic in terms of cosine of 3 pi over 5. So we could solve it with the quadratic formula. Note that A is 2 squared 4, B is negative 2, and C is negative 1. So cosine of 3 pi over 5 will equal negative negative 2, so 2 plus or minus the square root of b squared, which is 4, minus 4 times negative 1, all over 2 times 4, which is 8. So that simplifies to 2 plus or minus 2 root 5 over 8, which is 1 plus or minus root 5 over 4. Now, 3 pi over 5 is in quadrant 2. In quadrant 2, cosine should be negative. So the solution we're looking for is 1 minus root 5 over 4, which will be negative since the square root of 5 is bigger than 1. Question 14a, part 1. The two non-parallel vectors, u and v, satisfy lambda times u plus mu times v is equal to the 0 vector for some real numbers lambda and mu. Show that mu is equal to lambda is equal to 0. Alright, if we think about the statement, it should make a lot of sense that u and v are non-parallel and they've been multiplied by scalars and they're adding to 0. The only way for that to happen is if they were parallel. But how do we show it? Well, maybe we can try a proof by contradiction. Let's consider two cases. Would one of lambda or mu be able to be 0 while the other is not? If that were to happen, then one of these terms would become 0. So in this case, we'd have just mu times v is equal to 0. Now the only way for that to happen is for mu to be 0. So then let's assume that both of them are non-zero. Then that equation would mean that lambda times u would equal to the negative of mu times v. And then we'd have u is equal to negative mu over lambda times v, which would imply that they're parallel, since one is a scalar multiple of the other. But that's a contradiction because u and v are non-parallel vectors. Therefore, we can conclude that if that equation is true, both lambda and mu have to be 0. Part 2. The two non-parallel vectors, u and v, satisfy lambda 1 times u plus mu 1 times v equals lambda 2 times u plus mu 2 times v for some real numbers lambda 1, lambda 2, mu 1, and mu 2. Using part 1 or otherwise, show that lambda 1 is equal to lambda 2 and mu 1 is equal to mu 2. Alright, let's take that equation and move everything to one side to get the u's and the v's together. And we'll factorize. We can see lambda 1 minus lambda 2 as the lambda from part 1, as well as mu 1 minus mu 2 as the mu from part 1. And by part 1, if this is equal to 0, then both of those coefficients have to equal 0. And then that would mean lambda 1 equals lambda 2, and mu 1 is equal to mu 2. Now 14a continues with, the diagram below shows the tetrahedron with vertices A, B, C, and S. The point K is defined by vector SK equals 1/4 vector SB plus 1/3 vector SC, as shown in the diagram. The point L is the intersection of the straight lines SK and BC. Then part 3 is, using part 2 or otherwise, determine the position of L by showing that vector BL is equal to 4/7 of vector BC. Okay, let's work with the given equality and the diagram and see if we can set something up. So we have an expression for SK in terms of SB and SC. SK is 1/4 SB, so that's this here, plus 1/3 of SC, which is this here. Let's see if we can set up two expressions to get to the location of L. So those two vectors will get us to K, If we wanted to get the rest of the way to L, we can go from K to L. Now we could express KL as a scalar of SL. Maybe we'll call that lambda. Perhaps we can also get to L by taking SB and then BL. Notice that BL can be expressed as a scalar times BC. Maybe we'll call that mu. So, to get to L, we could take 1/4 SB plus 1/3 SC plus KL, which would be lambda SL. Or we could take all of SB plus BL, which is mu times BC. Now, if we want to use part 2, we know we need only 2 vectors, and then we essentially will equate the coefficients on both sides of that equation. So which of these vectors can we re-express? Well, both sides have SB, the right-hand side has BC. Let's look at replacing SC and SL. So SC is the same as SB plus BC. And SL is SB plus BL, which is mu BC. So let's collect like terms on each side. On the left-hand side, SB has coefficient 1/4 plus 1/3 plus lambda, and BC has coefficient 1/3 plus lambda times mu. And again, by part 2, we would know that 1/4 plus 1/3 plus lambda would have to equal to 1, and 1/3 plus lambda mu would have to equal to mu. Now the first equation gives us 7/12 plus lambda equals 1, so lambda is equal to 5/12. And then in the second equation, we have 1/3 plus 5/12 mu equals mu, which is 1/3 equals 7/12 mu. So mu equals 4/7. Now, what was mu? If we look back, we wrote BL is mu times BC. And we were trying to show what scalar factor BL is of BC. And we found that that is 4/7. Question 14a, part 4. The point P is defined as vector AP equals -6 vector AB minus 8 vector AC. Does P lie on the line AL? Justify your answer. Alright, let's see if we can put this onto the diagram to help us out. So we're only dealing with things that are in the base of this trapezium. So let's draw that triangle, ABC. L is on BC, and we found in the last part that BL is 4/7 of BC. So -6 AB would be going out this way, and -8 AC would be going out this way. And their sum would be here, that's P, and we want to know if P is on the line AL. It's hard to say, my diagram is just a rough sketch, so we're going to have to work that out. So, if P is on the line AL, what that means is the vector from A to P is a scalar times the vector AL. Let's see if we can determine if that's the case. AP is -6 AB minus 8 AC. And we want to know if that is equal to a scalar times AL. Now AL, we know, is AB plus 4/7 BC. Now, let's see if we can get this down to the same two vectors on both sides. Both sides have AB, and then we have AC and BC. Now, AC can easily be re-expressed in terms of AB and BC, since AC would be AB plus BC. So we have and we'll collect like terms. So if these two things are equal, then the coefficients of A would have to be equal, and the coefficients of BC would have to be equal. So if these two things are equal, then negative 14 would have to equal K, and negative 8 would have to equal 4/7 K. So if K is negative 14, does negative 8 equal 4/7 times negative 14? It turns out it does. So it is possible for P to lie on the line AL, since we found a value of K, a scalar multiple, such that AL is equal to AP. Question 14b. Let Jn be the integral from 0 to 1 of x to the n times e to the negative x dx, where n is a non-negative integer. Part 1. Show that J0 is equal to 1 minus 1 over e. Okay, let's take a look at J0. Now we can integrate that. And that's the result. Part 2. Show that Jn is less than or equal to 1 over n plus 1. So let's consider on the domain from 0 to 1, like our integral, what the function e to the negative x looks like. So between 0 and 1, e to the negative x itself is between 0 and 1. And it can include 1 but not 0. Now, what about x to the n times e to the negative x? Let's multiply by x to the n. Now, what if we set up an integral here? Well, the integral of 0 is 0. The middle is our expression Jn. And the integral of x to the n is x to the n plus 1 over n plus 1. So we have Jn is less than or equal to 1 over n plus 1. Part 3. Show that Jn is equal to n times Jn minus 1 over e for n greater than or equal to 1. Okay, remember that Jn is the integral from 0 to 1 of x to the n e to the negative x dx. We'll do the usual integration by parts here. U will be x to the n, so du is n x to the n minus 1 dx. dv will be e to the negative x dx, so v will be negative e to the negative x. So our integral will be equal to x to the n times negative e to the negative x. This part is outside of an integral now, so we'll write from 0 to 1, minus the integral of negative e to the negative x times n x to the n minus 1 dx from 0 to 1. Let's work out that first part and simplify the second part. We can see that integral as simply Jn minus 1, which is the result we're looking for. Part 4. Using parts 1 and 3, Show by mathematical induction or otherwise that for all n greater than or equal to 0, Jn is equal to n factorial minus n factorial over e times the sum from r equals 0 to n of 1 over r factorial. So part 1 gave us that J0 is equal to 1 minus 1 over e. Part 3 gives us Jn is equal to n Jn minus 1 minus 1 over e. Let's see if we can prove this with induction. Let's start with the base case of n equals 0. So in the statement given in part 4, we would get 1 minus 1 over e times 1 over 0 factorial, which is 1. So it equals 1 minus 1 over e, which agrees with what we got in the other definition of Jn. So it's true for n equals 0. Next, we'll assume it's true for some n equals k. We'll assume then that jk is equal to k factorial minus k factorial over e times the sum from r equals 0 to k of 1 over r factorial. Now let's see if we can prove it for n equals k plus 1. So our original definition of Jn would mean that j k plus 1 would equal to k plus 1 times j, k plus 1 minus 1 is just k, minus 1 over e. And we need to show that it's equal to k plus 1 factorial minus k plus 1 factorial over e times the sum from r equals 0 to k plus 1 of r factorial. So let's start with the left-hand side, that j k plus 1 is k plus 1, should be in a bracket, times jk minus 1 over e. And let's bring in our assumption. By our assumption, this would be k plus 1 times k factorial minus k factorial over e times the sum from r equals 0 to k of 1 over r factorial minus 1 over e. Well, let's see what happens if we expand the bracket. Let's just multiply the k plus 1 as one thing through that second bracket. Now, the reason I wanted to keep that k plus 1 as one thing together is because k plus 1 times k factorial is k plus 1 factorial. Now, the last thing to do to get this equal to this thing here. So what we're going to do is we're going to factorize the minus k plus 1 factorial over e from these two terms. So that would be the last term if the sum went from r equals 0 to k plus 1. So we could absorb it into the summation and say that it goes from r equals 0 to k plus 1 of 1 over r factorial. And that's what we were trying to show. So by the principle of mathematical induction, the statement has been proven true. Part 5. Using parts 2 and 4. Prove that E is equal to the limit, as n goes to infinity, of the sum from r equals 0 to n of 1 over r factorial. So part 2 gave us an inequality that Jn was less than or equal to 1 over n plus 1. It was also above 0. And part 4 gave us that Jn is n factorial minus n factorial over e times the sum from r equals 0 to n of 1 over r factorial. So let's put that expression into the inequality. Now we want to solve for e, since this is proving something about e. Let's multiply everything by e. And then we'll add the term with a summation. We'll subtract the e over n plus 1 to get the e terms together. Let's divide everything by n factorial, so on the right-hand side, we just have the summation. So let's take everything to the limit. Now, this fraction here, e over n factorial times n plus 1, if n goes to infinity, the denominator becomes infinitely large with a constant numerator. So that's going to go to 0. We'll see something similarly in here. As n goes to infinity, 1 over n factorial n plus 1 will go to 0. So, e is between the limits as n goes to infinity of that summation. N is both greater than it and less than or equal to it, which means e has to be equal then to that limit. Okay. Question 15a. A machine is lifted from the floor of a room using 2 ropes. The 2 ropes ensure that the horizontal components of the forces are balanced at all times. It is assumed that at all times the machine moves vertically upwards at a constant velocity. The machine is located in a room with height h meters. One of the ropes is attached to the point P on the machine and to the fixed point C on the ceiling of the room. The point C is a distance d meters to the left of P. Let the vertical distance from P to the ceiling be L meters, and let theta be the angle this rope makes with the horizontal. The other rope is attached to the point P and to the fixed point F on the floor of the room. The point F is a distance 2d meters from the right of P. Let phi be the angle this rope makes with the horizontal. Let the tension in the first rope be T1 newtons, the tension in the second rope be T2 newtons, the mass of the machine be m kilograms, and the acceleration due to gravity be g meters per second squared. Part 1. By considering the horizontal and vertical components of the forces at P, show that tan theta equals tan phi plus mg over T2 cosine phi. Okay, let's start with the horizontal components. These are only going to be coming from the tension in the ropes. So let's get the components, horizontal and vertical, for T1. So for this one, the vertical would be T1 sine theta, since the vertical is opposite of that angle. Horizontal would be T1 cosine theta. And then at T2, very similar, we'd have T2 sine phi on the vertical and T2 cosine phi on the horizontal. So horizontal, we have T2 cosine phi pulling to the right, T1 cosine theta pulling to the left. And then for the vertical, we have the tension in the ropes. We also have gravity. So in the up direction, we'll have T1 sine theta, and in the down direction, we'll have mg and T2 sine phi. So to get expressions that will result in what we want here, we're going to put the theta stuff on the left, the phi stuff on the right. So we can write the first equation, T1 cosine theta equals T2 cosine phi. And the second, we can write T1 sine theta equals mg plus T2 sine phi. Now we'll divide the second equation by the first equation. And then just simplify. Part 2. Hence or otherwise, show that the point P cannot be lifted to a position 2h over 3 meters above the floor. So let's draw a diagram to represent what would happen to P as it's lifted above the floor. Okay. Okay, as we lift P up, the ropes would approach forming a straight line. If they were to form a straight line, then we'd have equal angles here and here, and we'd have similar triangles. Now, the height of point P, if the ropes formed a straight line, would equal 2L due to similar triangles. And if that's the case, then the height of P above the floor would be 2/3 of H, since H is now split into 2L plus L. So this will equal to 2/3 H. So we know that when the point P is lifted so that the ropes form a straight line, that's equivalent to the point being lifted to 2/3 H. So what's happening as we have P approaching 2/3 of H? Once again, we have similar triangles. So those two angles, theta and phi, will be approaching each other in size, will be approximately equal to each other. And if that's the case, then tan theta will be approaching the value of tan phi. Now, from part 1, we had tan theta equals tan phi plus mg over T2 cosine phi. Now, if tan theta and tan phi are equal to each other, then they would cancel out on both sides, and we'd have mg over T2 cosine phi equals 0. mg is a constant. Cosine phi is also going to be a constant as we approach P. So in order for this fraction to equal 0, essentially T2 would have to go to infinity. which is not going to be possible. At some point, that rope will break, and we can't have an infinite force here. So that shows that P cannot reach the height of 2/3 h, because the closer it gets to that, the tension in your rope will have to go to infinity. Question 15b. Question 15 has some wordy questions in it. So, the diagrams show two positions of a single piston in the cylinder chamber of a motorcycle. The piston moves vertically in simple harmonic motion between a maximum height of 0.17 meters and a minimum height of 0.05 meters. The mass of the piston is 0.8 kilograms. The piston completes 40 cycles per second. What is the resultant force on the piston in newtons that produces the maximum acceleration of the piston? Give your answer correct to the nearest newton. Alright, so we're working with simple harmonic motion here. And we're working with force and acceleration. We know that F equals ma. Now, for simple harmonic motion, we have acceleration equals negative n squared times x minus c. Remember, we can find n by taking 2 pi divided by the period. Now, if the piston completes 40 cycles per second, that means its period is 1/40th of a second. So n is 80 pi. Also remember, c is the center of motion. The piston oscillates between 0.17 meters and 0.05 meters. So the center of motion is 0.11. So that means the force is the mass, which is 0.8 times negative n squared, 80 pi squared, times x, the position, minus the center, 0.11. Now, in simple harmonic motion, the maximum acceleration occurs when the position is at its peak or minimum. So we have max acceleration when x is 0.17 or 0.05. In that case, the force would be 3,032 newtons if we're rounding to the nearest newton. Now, depending on if you put in 0.17 or 0.05, you get a negative or a positive, the same value. And that's the answer. Question 15c. Using the substitution x equals tan squared theta, evaluate the integral from 0 to 1 of sine inverse of the square root of x over 1 plus x dx. Alright, so our substitution is x equals tan squared theta. We'll also need dx. So dx would be 2 tan theta times secant squared theta d theta. Since this is a definite integral, let's find the limits of integration for theta instead of x. Now, as x goes from 0 to 1, what does the argument for sine inverse go between? At 0, the square root of 0 over 1 is 0. And then at 1, it's going to be the square root of 1 over 2, 1 over root 2. So if that's what's going to go into sine inverse, we're going to be producing angles from 0 to pi over 4. So if the inputs to sine inverse are going through from 0 to 1 over root 2, then sine inverse is producing angles from 0 to pi over 4. Remember, the range for sine inverse is negative pi over 2 to pi over 2. And if we look at x equals tan squared theta, when x is 1, we get tan squared theta equals 1 Normally, we'd have to look at square rooting that and getting plus or minus 1, but we know we're looking in quadrant 1 right now. So in that case, we'll have theta being pi over 4. And then when x is 0, tan squared theta equals 0, so we're going to get theta equals 0. So those are our new limits of integration. So let's substitute into this integral. We'll now be integrating from 0 to pi over 4 of sine inverse of the square root of tan squared theta over 1 plus tan squared theta times 2 tan theta secant squared theta d theta. Now, from our Pythagorean identities, we know 1 plus tan squared theta is secant squared theta. So inside that square root, we're going to have tan squared over secant squared, which is essentially sine squared over cosine squared divided by 1 over cosine squared. So that simplifies to sine squared. And of course, we're square rooting that, so it's going to be sine inverse of sine theta. So we're just going to get theta itself. I can put the 2 in front. Okay, that's a bit of a weird integral, but we could consider integration by parts, since theta is kind of like an x. If you make that the u, that derivative, it'll disappear. And we can integrate tan secant squared d theta, so that could be our dv. So u is theta, du is just 1 times d theta, dv will be tan times secant squared theta, d theta, so v will be, now of course the derivative of tan is secant squared, so it's a bit of a u substitution. We're essentially integrating u, which will be u squared over 2, so it's going to be 1/2 tan squared theta. Okay, so we get uv, so we have 1/2 times theta times tan squared theta, and that comes outside of an integral, so we're going to write that's from 0 to pi over 4 minus the integral of v du, which is going to be the 1/2 tan squared theta d theta. And let's not forget that factor of 2 that was in front of the entire integral. Okay, let's evaluate that first part, and then to integrate tan squared, we're going to write that as secant squared minus 1. So we're going to get 2 times 1/2 times pi over 4 times tan of pi over 4 squared, and tan of pi over 4 is 1, and 1 squared is 1. And then when we plug in 0, it's just going to be 0. And then we rewrite this again as secant squared minus 1. That's really easy to integrate. Remember, the derivative of tan is secant squared, so it's a simple integration there. I'll distribute the 2 through to cancel out some of those halves. So we're going to get pi over 4 minus, and again, the integral of secant squared then is tan, and then the integral of 1 is just going to be theta there, and we're going from 0 to pi over 4. I'll fix that there. That's pi over 4. Okay, so we've got pi over 4 minus, now we've got tan of pi over 4, which is 1, minus pi over 4, minus tan of 0 is 0, and then plugging 0 into theta is 0 as well. So when we distribute that minus through, it's going to be pi over 4 plus pi over 4, so pi over 2, and then minus 1. And that's the answer. Question 15D. The complex number z satisfies the modulus of z minus 4 over z is equal to 2. Using the triangle inequality or otherwise, show that the modulus of z is less than or equal to root 5 plus 1. So, if you like, you could do a quick sketch to help see where the triangle inequality comes in here. So if we just draw an arbitrary complex number z, then what would 4 over z look like? Well, we would take 1 over z and then times it by 4. So 1 over z would be here, and then 4 times its length. And then z minus 4 over z would be this here. And we are restricted to the length of this difference being 2. Okay, so by the triangle inequality, we'd have the length or modulus of z minus the length or modulus of 4 over z, all in the absolute values, would be less than or equal to what we have. So the absolute value or modulus of z minus 4 over z, which is less than or equal to, now just separate the absolute value of z minus 4 over the absolute value of z. Now we're given that that middle one is equal to 2. Now, we know from working with absolute values and inequalities that this part of the inequality here would say that the inside of the absolute value there on the left is between -2 and 2. One thing we could do here is multiply through everything by the modulus or absolute value of z. Let's add 2 times the absolute value of z to everything. So we have 0 on the left. Now, let's focus on this part of the inequality, the fact that this expression on the middle is less than or equal to 4 times the absolute value of z, so that if we rearrange it, we would have absolute value of z squared minus 2 times the absolute value of z minus 4 is less than or equal to 0. We could see this as a quadratic. Let's find when it would equal to 0, so we can then find out when it's less than or equal to 0. So by the quadratic formula, -2 plus or minus the square root of 4 minus 4 times 1 times -4 all over 2. So that becomes 1 plus or minus root 5. Now, it's quadratic. If we think of it as a parabola, it's up-facing with roots 1 minus root 5, 1 plus root 5. So when is it less than or equal to 0? And that's going to be between those two roots. Now, the absolute value of z is also the modulus, is the length of distance from the origin. It has to be positive. So we're going to restrict ourselves from 0 to 1 plus the square root of 5. So that means that the modulus of z, absolute value z, is less than or equal to 1 plus root 5. Question 16a. A square in the argand plane has vertices 5 plus 5i, 5 minus 5i, -5 minus 5i, and -5 plus 5i. The complex numbers za equals 5 plus I, zb and zc lie on the square and form the vertices of an equilateral triangle, as shown in the diagram. Find the exact value of the complex number zb. Okay, I might sketch the axes on this diagram. 5 plus I is 5 to the right and 1 up. Okay, this is an equilateral triangle, so the angle in each corner is 60 degrees or pi over 3. So what I'm going to notice is that ZC minus ZA is going to be ZB minus ZA rotated clockwise by pi over 3. So ZC minus ZA is e to the pi over 3I times ZB minus ZA. And let's note that e to the pi over 3I is equal to 1/2 plus root 3 over 2I, which we can get from our exact value triangles. Now, let's see if we can express ZB in terms of components. We know its imaginary component is 5. What about its real component? So for now, we can call it the real component of ZB. And we can do something similar for ZC. So we're going to let ZC be the real component of ZC minus 5I, and ZB be the real component of ZB plus 5I. So we will put all of that into this expression or equation that we've got. We'd get, we know what ZA is, 5 plus I. Okay, let's simplify a little bit. Now, I may just multiply through both sides by 2, so I don't have to work with fractions on the expansion on the right. I'm just kind of gathering the real stuff together and then the imaginary stuff. Note that I squared is -1. Okay, so we can see that the imaginary components only involve the real component of ZB. So if we set those equal to each other, we'll be able to solve for the real component of ZB. So on the left-hand side, it's just the -12. On the right-hand side, it's 4 plus root 3 times the real component of ZB minus 5 root 3. So we have the real component of ZB. We already know its imaginary component since it's on the square at a real component of 5. So ZB is 16 over root 3 minus 5 plus 5I. 16b. A projectile of mass m kilograms is launched vertically from a horizontal plane with initial speed v0 meters per second, which is less than 100 meters per second. The projectile experiences a resistive force which has a magnitude of 0.1 mv newtons, where v in meters per second is the speed of the projectile. The acceleration due to gravity is 10 meters per second squared. The projectile lands on the horizontal plane 7 seconds after launch. Find the value of v0, correct to 1 decimal place. Okay, with this kind of question, we're going to have both the upward journey and the downward journey to worry about. So in the upward journey, we're going to have mg and 0.1 mv acting both in the opposite direction to the upward journey. Downward, mg in the direction of travel, and 0.1 mv opposite to it. All right, let's start with the upward journey. So we have our forces. minus mg and minus 0.1 mv. Now, the m's will cancel out, and g is 10. So we have acceleration equals negative 10 minus 0.1 v. Now, we want to know what is the maximum height of the projectile so we can use that in its downward journey. On the formula sheet, we can see the acceleration is v times dv dx, which will allow us to get an expression in terms of v and x. And we're going to use that because we know that the maximum height occurs when velocity is 0. So if we have that expression in terms of v and x, we'll set v to 0 and solve for x. So let's make things a little nicer, and we can factorize out the minus 0.1. And then let's separate those variables. Integrate both sides. On the left, what we could do is add and subtract 100 to the numerator. And we'll separate out the minus 100 to its own fraction. So that's going to be the integral of 1, which will be v minus 100 ln of 100 plus v. And on the right-hand side, we get negative 0.1x plus a constant. Now, for the constant, we know that when t is 0, v is v naught, and x is 0. So we'll get v naught minus 100 ln of 100 plus v naught is equal to 0 plus c1. And because v is going to be positive, I'm not going to need to use the absolute values here on the log. So we have c1. Let's put it all together. And as we were saying, maximum height occurs when velocity is 0. So v will be 0, and then we could solve for x. So we'll just move those terms to the other side and use some log laws to put those ln's together. So we'll get x is 10 v naught minus 1000 ln of 100 plus v naught over 100. So that's the max height of the projectile. Now we can look at the downwards journey. So in the downwards journey, we'll make down positive. Our forces are gravity, which will be going in the same direction as our journey, so it's going to be positive. And then we have resistance in the opposite direction, minus 0.1 mv. So acceleration, our m's cancel, g is 10. So what we have is the height that it needs to fall, which is equivalent to the max height on its upward journey. We also know the time that it will hit the ground. So we need an expression involving x and t, which will then allow us to solve for v naughts. So if we want x and t, we'll just use the regular dv dt for acceleration. We don't have the none anymore here. Now, this still involves v. We'll still have to do a separation of variables. Let's factorize out 0.1 first. And then we'll divide that to the other side. And integrate both sides. So this is going to be a log minus ln 100 minus v. And this is going to be 0.1 t plus a constant. Now we do know that v is less than 100, so then we can drop those absolute values. And we know that when t is 0, v is 0 because we are starting at rest after we've hit the maximum height on the upward journey. So we have minus ln 100 minus v equals 0.1t minus ln of 100. Let's solve for v so we can then get back to x. Let's take both sides to the exponent on e. That'll simplify. So v equals 100 minus 100e to the negative 0.1t. Now, this is in terms only of t now, so we can just integrate to get x. So x is 100t plus 1000 e to the negative 0.1t plus a constant. Now, when t is 0, x will be 0. So that gives us C3 negative 1000. So x is 100t plus 1000 e to the minus 0.1t minus 1000. Okay, now we know the distance it needs to fall, and we know that the projectile hits the ground 7 seconds after it's projected. What we need to think about is that includes the time in its upward journey. So we need to find the time that it reaches its max height and subtract that from 7 to get the time that it's going to take to hit the ground after it reaches its max height. So if we go back to acceleration during its upward journey and get an expression for v in terms of t, we can get that time we need. So in this case, we can use dv dt again, factorize out negative 0.1, and separate variables. Now the integral will be ln 100 plus v minus 0.1t plus a constant. Now, on the upward journey, when t is 0, v is v naught. So C4 is ln of 100 plus v naught, and so we have ln of 100 plus v equals negative 0.1t plus ln of 100 plus v naught. Now again, max height occurs when the velocity in the upward journey is 0. So when v is 0, we can solve for t. I can absorb that negative into the log so it looks a little nicer. So that's the time when it reaches max height. So the time on its downward journey will be 7 minus this time, which is the time of the maximum height. So the time it takes to hit the ground on this downward journey will be 7 minus the time it takes on its upward journey. Okay, let's go back to x for the downward journey. We now know how far it needs to travel. That came from the max height, and we also know the time it takes to do that. So this here was the max height, so our distance as well for our downward journey. So I'll put that there, and that's going to be the left-hand side of this equation, which is x for our downward journey. Then for the right-hand side, we're going to plug in our time. Okay, let's solve for V naught. The negative 1000 ln's will cancel on both sides. E to the ln will also cancel here. So we'll have 10 V naught on one side, 700 plus 1000 e to the negative 0.7 times 100 plus V naught over 100 minus 1000. So this will simplify a little bit to 10. We can move the V naught term to the left-hand side. So we'll have the 10 V naught, and then we're going to subtract the 10 e to the negative 0.7 times the V naught. On the right-hand side, we have the 700 minus 1000, and the 10 e to the negative 0.7 times the 100, so plus 1000 e to the negative 0.7. So to solve for V naught, we'll factorize that left-hand side for V naught, and then divide. Let's calculate. So we get 39.1, rounding to one decimal place, meters per second. Question 16c. It is given that for positive numbers, x1, x2, x3, xn, with arithmetic mean a, x1 times x2 times x3 times times xn divided by a to the n is less than or equal to 1. Suppose a rectangular prism has dimensions ABC and surface area S. Part 1. Show that A times B times C is less than or equal to S over 6 to the power of 3 over 2. Okay, let's get an expression for the surface area of the rectangular prism with the dimensions A, B, and C. The surface area would be 2AB plus 2AC plus 2BC. Now, if we turn this expression into an arithmetic mean, we are adding 6 terms, 2 AB terms, 2 AC terms, and 2 BC terms. So A, the arithmetic mean, would equal S divided by 6, since again there are 6 terms being added. Now, according to the given statement, if we multiply all of these terms together, AB times AB times AC times AC times BC over the arithmetic mean to the power of n, there are 6 terms, so over S over 6 to the power of 6, that would be less than or equal to 1. So this simplifies to A, B, C to the power of 4 over S over 6 to the power of 6 is less than or equal to 1, which gives us ABC to the power of 4 is less than or equal to S over 6 to the power of 6. And then taking the 4th root of both sides to the power of a quarter, ABC is less than or equal to S over 6 to the power of 6 to the power of 1/4. And then, of course, using index laws, that is S over 6 to the power of 3 over 2. Part 2. Using part 1, show that when the rectangular prism with surface area S is a cube, it has maximum volume. So let's say all sides are A. Our inequality becomes A times A times A, so A cubed, is less than or equal to S over 6 to the power of 3 over 2. Now, If it is a cube, the surface area is equivalent to 6 times a, or a squared. So now we have a cubed is less than or equal to 6 times a squared over 6 to the power of 3 over 2. And then that simplifies. So we have a cubed is less than or equal to a to the power of 3, and a cubed is its volume. So we have that its volume is less than or equal to a cubed, but we know its volume is equal to a cubed. So if a cubed is the upper limit here, then the cube has the maximum volume. Question 16D. Find all the complex numbers z1, z2, z3 that satisfy the following three conditions simultaneously. First, the modulus of z1 is equal to the modulus of z2 is equal to the modulus of z3. Second, z1 plus z2 plus z3 equals 1. And lastly, z1 times z2 times z3 equals 1. Okay, let's see what we can learn from putting the first and third facts together. We know that the product of the three complex numbers is equal to 1. And let's consider the modulus of the product. So the modulus of the product will equal 1. And we could split up the modulus over the product of the three complex numbers. That tells us that the product of their moduli is equal to 1. Now the first fact comes in to tell us that all three moduli are equal. And the only way for this to happen then is for the moduli of each of the complex numbers to be 1. Now, since their moduli are all 1, if we need to take 1 over any of these complex numbers, it will be the same as the conjugate of that complex number. So if we come back to that third fact, we could perhaps divide z1 to the other side. And as we said, since the modulus is 1, this will equal to the conjugate of z1. Now, we could obtain similar results for the other three complex numbers. Now let's consider the sum of these three facts. Now we know that conjugate is able to be separated over addition, and so it can also be recombined over addition. And we already know that the sum of the three complex numbers equals 1. The conjugate of 1 is 1. Now at this point we have three facts that are going to lead us to the next part. We know that the sum of the three numbers is equal to 1. We know that the sum of their pairwise products is equal to 1. And we know that the product of the three is equal to 1. Now, you may recognize these three facts from something we talk about in polynomials. They are sometimes known as Vieta's formulas. The three facts that we have now match with the three Vieta's formulas for cubic polynomials. And that means z1, z2, and z3 are the roots of that cubic polynomial. Now, let's make sure we put these coefficients in correctly. Remember that the sum of the three roots is equal to negative b over a. The sum of the products of the pairs is equal to c over a. and the product of the three roots is equal to negative d over a. Now, this is a complex valued polynomial, so we may use z for the pruning rule, and we'd have z cubed setting a to 1 minus z squared, since negative b over a is positive 1, that means this coefficient is negative 1, plus z, since c over a is positive 1, minus 1, since negative d over a is positive 1, the constant is negative 1, equal to 0. Now, we can solve this complex valued polynomial. We can, of course, factorize by grouping. And the roots would be, of course, plus and minus I coming from z squared plus 1 equaling 0. Now we can arbitrarily assign each of these values to be z1, z2, and z3. And that's the answer. Thanks for watching, and I hope it was helpful for you. Make sure you like and subscribe. We'll be putting more content out for HSC students, including work solutions and other content. If you have any questions about any of the working out, feel free to leave a comment. Have fun studying, and good luck on your exams!